Another question which I want to discuss with you, question 30. It's again I can link this question to my two lemmas, intersection lemma and orthogonal complement lemma. But the reason I chose this question is that because it discusses polynomials, and we haven't discussed with you the polynomial vector spaces or polynomial subspaces yet. So look at this. The question says, consider that's the subset we have to address. We have to prove that this is a subspace. It's the first time I use this symbol, P free of R. It's the first time I use this symbol. When we discussed with you vector spaces on Thursday, I gave you a few canonical examples of the vector spaces. P free of R, it's another one which should go on that list. It's another example of the canonical vector space. That is how it is defined. Here's my quadruple. Remember, when you think of a vector space, you always think of a quadruple. And that's my quadruple. Plus dot. And my scalars are Pn of R itself. It's a set of polynomials of degree n or less. So it's a set of functions of this structure. You see, it's a set of functions of this structure. That's a polynomial of degree n or less with coefficients real numbers. It's set here. Real numbers, it's set here in this notation. If you have two polynomials, you add them pointwise. So if you add two polynomials, you build a new polynomial by doing pointwise addition, like so. And when you scale polynomial, you also do it pointwise. That's how you scale a polynomial. So you see, I'm using this opportunity of question 30 to also give you the definition of this, another canonical example of the vector space. I'm not going to check the axioms, 10 axioms for this vector space. The argument, something we did with you on Thursday, I mean, basically that argument can be repeated here as well. The interesting thing about this, the interesting thing which you will observe very often with the polynomials is that they resemble a lot the n tuples, because when you add two polynomials, effectively, basically, you add the corresponding coefficients. Or when you scale a polynomial, you scale the corresponding coefficients individually. And that's a resemblance between the Pnr and Rn plus 1. It's not a coincidence. It's a good resemblance which I will remember all the time, and I suggest you keep this in mind all the time. So basically, polynomials can always be converted or replaced in a vector space context with the n plus 1 tuple of numbers, like this, which consist of the coefficients of that polynomial. And everything you do with the polynomial as a vector can be done similarly with this n plus 1 number, n plus 1 tuple of numbers as a vector. Now listen how we're going to argue question 30. Again, if you do this question in your tutorial, your tutor will probably argue this question via subspace theorem directly, but my job today to make the linkage to the intersection lemma and orthogonal complement lemma. Here's the linkage. Look at this. Imagine I have a polynomial of degree at least 3. Sorry, at most 3. So imagine I have a polynomial from this of degree 3 or less. Is the explicit form of that polynomial. I want to see what happens if I put this polynomial into this condition. I will mark this condition with the asterisk. So derivative of such polynomial, we all know how to compute the derivatives of power functions. Here's a derivative. Here's my derivative. So if I take this p, and if I take this p dash, and if I sub it in here, that's what I'm going to obtain. My asterisk condition will be equivalent to the line like this. It's a long line. Let's just take it slowly. Here's my sub for the p dash. Well, I made a typo, right? Stupid. Here's my sub for the for the P. And so my asterisk condition, it should be satisfied for every x. So basically that's my asterisk condition now in explicit form. As you observed, there's a typo here, there's a 2 here, there's a 3 here. Now I have to decide what to do right now, because I thought this discrepancy 2 or 3, it will affect my further computations. Let's just fix it. I can actually make 2 here, because from the conceptual point of view it doesn't make any difference. But probably let's just keep it 3. Do we have time for that? Yeah, we do have time for that. Let's just fix this typo. It will be 3 here. So if I do the expansion now, if I do the complete expansion, if I assemble now all of the coefficients with the all of the x's with the identical powers, then, well, it will be different this time. It will be different this time. I'll open what I have, but keep in mind that what I have here is not the correct answer, because now I fixed the typo. I'm gonna take you through this again. I'm gonna fix it. Let me just open it first. That's what I had before, but this is not exactly right, because, for instance, look at this x cubed appears here with the coefficient 3a0, because it's x squared times this x, and here we have negative 3a0. So in fact, x cubed will be missing. X cubed will be missing from the whole expansion. So I have to kill this. I have to kill this. Now, what happens with x squared? X squared will appear, how many times x squared will appear? 3 times x squared will appear. It will appear when you multiply this. Oops, sorry. I'm sorry. It will appear 3 times. One time it's when you multiply this this x squared with this 1, and that will be coefficient 3a0. Second time it will be when you multiply this one with this x, it will be coefficient 2a1. And the third time is when this negative 3 is taken next to this a1. So altogether, what I see now is that I have to put x squared will come with the coefficient. Let's just fix the coefficient now. The coefficient will be negative a0 will be coefficient 3a0, negative a1. Yeah, that's the correct coefficient next to the x squared. Let's just see what is the correct coefficient next to the x. X will appear 3 times again. One time it will appear when this one is multiplied by this 1. It's 2a1. It's good here. Second time it will appear when you take this, this a2 next to this x. And the third time it's this negative 3. So in fact I have to put 2 here to correct my coefficient. And the last one, the 3 coefficient appears only twice. It's this one with this a2 and this negative 3 with this a3. So it actually here will be 2 should go into 3. And that's the correct expansion of the asterisk condition. Now my polynomial equals 0 identically for every x means that every coefficient individually equal 0. Yeah, every coefficient individually equals 0. Let's just do this. Not 3a not take a1 equals 0. That's the first condition I have. Second condition I have a1 take a2 equals 0. It's the second condition I have. And the third condition I have is a2 take 3a3 equals 0. Here we are. So let me just summarize what just happened. We studied this set from the question 30, and that's a set of polynomials subject to such condition. And I decided to restate the condition in terms of the coefficients of that polynomial. So what did I do? I just chose these names for my coefficients, or this quadruple of numbers for the coefficients. I plugged in my polynomial into the condition, and here's the conditions on the coefficients we have come up with. Now, each of these conditions individually, if you just put it in here, this is the orthogonal complement subspace condition, isn't it? This is a condition, this is a condition, which is equivalent to This is a condition which is equivalent to subspace S R with a vector 3, -1, 0, 0. And that's why the polynomial subject to this condition alone, forget about the rest of it, it's a subspace. It follows from this from the orthogonal complement subspace lemma. This condition, it's another orthogonality condition. Here it is. It's the vector 0, 1, -1, and 0. And this one again, it's again orthogonality condition. Here it is. It's the vector 0, 0, 1, and -3. Now what we can say about the S itself? This space S itself, or the set S itself, it is because it's a subject to these three conditions simultaneously, it will be the intersection of these three subspaces. And we know from the subspace, from the intersection of subspaces lemma, that when you take the intersection of subspaces, that will be another subspace. And that's why this S is a subspace.